In the investigation of the Idaho student murders, a single digital footprint has ignited a massive forensic battle. It is a log recorded at exactly 3:51 and 3 seconds a.m. on a surviving roommate's phone. Early public narratives dismiss this as random user activity or unexplainable system noise. But when you apply raw software engineering to the unsealed files, the code tells a completely different story. It reveals a flawless, real-time machine response to an event happening right outside the house. To understand this log, you cannot look at the data fields in isolation. In digital forensics, analyzing single fields leads to false conclusions. If you look only at the name, you get lost in internet speculation. To find the truth, you must interpret the log holistically, as a unified data row where the structure of one column defines the physical meaning of the next. Let's address the elephant in the room. A massive portion of the true crime community looks at this exhibit and thinks Dylan was actively typing or editing a saved contact inside her phone's address book app. That is a complete misunderstanding of mobile architecture. Look at the data structure. The left column lists the category as contacts, and the file path on the right ends in table, ZCONTACTS. This is not a user directory. This row lives inside Interaction C, DB, a hidden system database belonging to Apple's Corduet framework. The user cannot see this database, open it, or type into it. In iOS design, this contacts table is an automated background ledger used strictly by the operating system to log background application hooks, network entities, and system-level interactions. Dylan didn't save a contact at 3:51 a.m. The phone's root operating system did.
Let's be completely clear. This is not a theory. It is not armchair detective speculation, and it is not internet pseudoscience. This analysis is based entirely on documented, industry-standard iOS logic and the fundamental principles of how mobile operating systems are engineered. These background systems are purpose-built by manufacturers like Apple to behave exactly this way by design. The code is real, it is public, and it is common to billions of devices worldwide. Mobile operating systems do not spontaneously manifest fake transaction states. Because of the rigid constraints of this specific data log and the independent visual anchor of the 1112 camera, there are exactly two, and only two, technically possible engineering scenarios that could have written this entry. Both require a live, real-time external trigger. Now look at the middle column, which provides the structural anchor. The timestamp reads 3:51 and 3 seconds a.m., and the status is explicitly marked created. In database execution, created means a brand new data row was generated and committed live at that exact microsecond. This completely eliminates routine system maintenance sweeps, which rely on status tags like cleaned or indexed. Now look at the metadata block on the right. The file path maps down to a raw hexadecimal byte offset of 0x3C0E0 and captures the exact database size of 5,537,792 bytes at that millisecond. Notice that there is no application bundle or app ID text appended anywhere in this metadata. The data drops directly from the source log to the raw system database table schema. This layout is the literal visual proof that the event bypassed the user interface entirely. It was written directly at the root daemon level of the operating system. Look closely at the thin, vertical grid lines at the bottom of this data block. They are cleanly clipped at the top, but they continue open-ended past the bottom of the row. This is the exact visual signature of a cropped spreadsheet export, proving that this 3:51 a.m. entry is the literal head of a continuous string of digital records. From a systems programming perspective, this sequence reveals the exact relationship between the physical world and mobile operating system logic. Mobile devices are event-driven to preserve battery. Root system daemons sit in a low-power state waiting for an external prompt. At 3:51 and 3 seconds a.m., an external network broadcast delivered a live data packet that hit the device's hardware interface. Technically, this could have happened in one of two ways. It was either a localized, peer-to-peer proximity handshake from an active app passing by the wall, or a real-time cellular server push event triggered by an external driver's arrival status update. But the exact wireless vector is ultimately irrelevant, because the downstream system logic remains identical. This incoming external payload forced the operating system to instantly wake up from its low-power state, process the inbound metadata token, and commit that live, real-time row to the database.
In iOS architecture, when a root daemon is forced awake by an external network event, it immediately triggers a cascade of pending background tasks to maximize system efficiency. The string of data flowing directly below this log, indicated by those continuous grid lines, represents those subsequent system cleanups, cache flushes, and database indexing sequences. The maintenance string is merely the symptom. The external network broadcast is the live catalyst. You cannot have the cleanup without the initial hardware trigger waking the system up first. When you stop viewing the log as random system noise and analyze it as an interconnected network event, the physical evidence locks cleanly into place. At exactly 3:51 and 27 seconds a.m., the 1112 neighbor camera captures the courier on foot. The tiny 24-second window between the digital created log at 3:51 and 3 seconds a.m. and her physical presence on screen is all the proof you need. The state has the corporate records, but by hiding how the local device hardware reacted to that code, they are trying to keep a live witness silent. If you are a programmer, a software engineer, or a digital forensics expert, I invite you to pull up the unsealed court files, look at this row schema layout, and validate these architectural findings yourself. Examine the Corduet framework, check the database injection mechanics, and leave a comment below with your analysis. Let's make the data talk.